depending on where you're at, everybody. So topic today is how to win $1 million math prize, which I should warn you ahead of time. There will immediately be, oh my goodness, a number of qualifications to that. But the problem itself is certainly an interesting one and well worth taking a look at. So let's dive into it here. Quarter of a century ago, 25 years now, a little bit over 25 years, the Clay Math Institute came up with 7 Millennium Prize problems. This was reflecting an idea that had been done a century earlier. And each one had a nominal prize of $1 million. A fellow named, and I will not pronounce this correctly, Grigory Perelman solved one of them very quickly in 2002, which was the Poincare conjecture. And of course, there's a marvelous story with that, is that he simply wasn't interested in the money. He refused to accept the prize. For him, the math was the entirety of what he was trying to do, and he kind of didn't care. And I found that striking. Even Richard Feynman almost boycotted the Nobel Prize committee once, which was he backed off from that. But that was a similar example that comes to mind. So that leaves 6 prizes. Actually 2 of which stand out, but one I'll point out because it stands in a slightly different way. 2 of them are really physics problems. And one of them is really a physics problem, as in deep particle physics, and not something you would normally expect for a math prize. So the name of this one is the Yang-Mills Positive Mass Gap Challenge, which is a kind of a mouthful in terms of trying to understand what it's talking about. So let's dive in. Part 1, warnings. As I said, there's a lot of these things. I'm surprised myself when I dig into it. I go like, oh, there's some interesting details here that I kind of missed the first time around on that. And this is definitely one of those cases. The first warning is, if you win, don't make plans, don't buy a house, don't expect to get that money anytime soon. You will be lucky if you get that money in 10 years because of the way that the winning criteria are defined. So this is not something you can plan on. There's an absolute minimum of 2 years according to the rules, but the real barriers are that you have to get it improved by an appropriate math journal, which CMI determines what are appropriate math journals. CMI will not participate, will not help, will not add any information. They basically say, well, when we see something that we like in the journals, we will award the prize. So that produces quite a bit of delay in terms of trying to get one of these prizes. So you can see the information there. There's a set of rules. There's a qualifying outlet. That's where you get into this whole publication strategy becomes an issue with that. Here's the official summary, quick summary of the CMI prize rules. No direct submission, no further guidance. All 3 of the following. It must be published in an outlet. You have to have a couple years about, that's where you get the minimum of 2 years, absolute minimum of 2 years. Of course, it's going to take you more than, a week to publish it, to say the least. And so even if you just literally solve this thing today, you'd still have quite a bit of time before you could go to it. And then there's that final qualifier: proposed solution must have received general acceptance on the global mathematics community. This is an interesting qualifier if it turns out, as some people like Nobel laureate David Gross has speculated, it's going to require a radical reorganization of mathematics to do it, which is, I just find that amusing because you get this kind of this kind of catch-22 that, well, yeah, so if your solution that actually does what you want it to do requires that you do some massive overhaul of precious concepts to the mathematics community, how long is it going to take you to get global mathematical acceptance? The answer is it's probably going to take a lifetime because these things move slowly. So this is why, again, you say, even if you have a solution to this prize, don't be betting your house on it. Yeah, some of the bluntest criticisms, and this surprised me. This was a find, actually kind of delayed my presentation when I encountered this marvelous video coverage, a presentation that David Gross, 2004 Nobel laureate, had about talking about this problem. So he was addressing the same topic that I'm addressing today, except from an enormously deep perspective of being really in to exactly the right physics. So I mean, it's just an astonishing bit of work. And he was grumpy. So he he started out this whole presentation grumpy. There's no other description for it. So he puts in things like, he puts in little remarks like he says, before they fired him, they came up with this idea of this. And David Gross was highly cynical, is highly cynical that about the nature of these prizes. So from his perspective, it's interesting. He takes the prize seriously, but at the same time, he says, like, this was a PR stunt. This was something to get millions of dollars of publicity. Because you think about it, I never heard of Clay Math Institute before this, and neither did a lot of other people. So it worked. They got a lot of publicity out of that. They had one prize that they awarded, and again, he was a little grumpy in this. He was sort of like, I think they knew I think they knew ahead of time he wouldn't accept it. So the cynicism here goes deep in terms of that. But again, look who this is coming from. David Gross, more than any other person, is the man and the team and the background of the people who are working this very problem from a physics viewpoint. So it's not it's not a casual issue in that case. I should point out, one of I read the Nobel laureate lecture by David Gross, and I just loved it because he's a little bit of grumpiness seems to be a characteristic there, but he talked about the fight that he and his comrades had to do against what was called S matrix theory at that time. And if you've never heard of it, you may have heard of it. S matrix is like the incarnation in the idea that the universe is all math. So it says that if you get down to a certain level, everything below that level is pure math, pure math. And that was the dominant theory at that time. That was where everybody went. The S matrix was a scattering matrix. It shows you when you bump particles into each other, they scatter in certain ways. And the premise was that that's it. It doesn't go any farther. You just have these little matrices of scattering, and I find that uh, David Gross and company came up with a very, very different perspective, which was to uncover an entirely new style of force. We're all familiar with electric and magnetic forces and how those work. He found this strange force, which we now call the color force, sometimes a strong force, depending which level you look at. He found this, they found this strange force that it acts much more like a rubber band. And a rubber band, you stretch it apart, it gets tighter and tighter until it breaks. But when you go together, it just loses all bonding. And that is what this new force acted like, what we now call the color force. So it was an intriguing discovery that they had. And he was not the only one who did it. There was a number of people were involved in this, the origin of this, but they're the ones who really first captured it and qualified that. So this deals directly with some of the same issues of how do these particles work, and it gives them a unique perspective on that. And also maybe a little bit of cynicism about taking a pure math approach, because what he found was the S matrix just didn't work. It didn't track the actual physics beyond a certain point. It was superficial. It covered an aspect of the physics, but then you get in farther and the reality is a little more complicated, and it always bumps the math models and pushes them in a different direction. So that was kind of where his background came from. Warning number 3. This one baffled me, and it still baffles me a little bit. There's a very simple statement of the Yang-Mills problem, which is that the particles called gluons, which many of you I'm sure have heard of, have mass. That's it. That's actually captures pretty much all of the verbiage and all of the long, like pages and pages of description that are done from a mathematical viewpoint. But the actual idea is that even though gluons in the models we currently have no mass, they're like photons. In fact, they're very closely related to photons. So like the photons, they have no mass. They're supposed to have indefinite range, except that they don't. So people have always been a little uncomfortable with that and said, like, why do these things act like they're short range, like the weak force? Weak force explicitly has mass, unambiguously is a short range force because of that mass. And the gluons kind of behave like that, but nobody could really pin it down experimentally. And nominally, the models all said they should have no mass. They should just be like a lot like photons. So that caused a lot of consternation with that. And in the 70s, the humorous terminology in the 70s, gluons, you stick things together with gluons. They come in 3 colors and 4 flavors, and that's real physics terminology. I'm not making that up. I remember I had one friend who I just started doing that, like I was making up. Yeah, the basic components of the universe are quarks, and they come in 3 colors and 4 flavors. And of course, she completely thought I was making this stuff up at the time, but they had a very whimsical bent back during that time period and left us with some nice names. The color terminology is also extremely appropriate. It describes the properties in a surprisingly good way in terms of how they mix with each other. So the Yang-Mills challenge is prove that gluons have mass, but the qualifier is, as far as the CMI is concerned, this is a math problem, but it's actually a physics problem. So you see a little bit of a paradox there. It doesn't matter what your math says. If you do the experimentation, you find out that they do or they do not have mass. That's reality talking. That's independent of whether the math did or did not predict it. So a little bit of clarity on that would have been very nice up front on these concepts, and just come right out and say it. Say that, yeah, okay, we're trying to say that gluons, unlike photons, have mass. I think most people can glom onto that a lot faster, and then you can get into the mass gap and all the other specific terminology, which is really just another way of saying the same thing. Because when you talk about a mass gap, you're saying that the gluons have a mass. So just like electrons and positrons, if you don't have enough energy, you can't make a gluon. That's the mass gap right there, is that the gluons can only come into existence at certain energy levels. It's like a step versus a ramp. Photons have a ramp. They can be as smooth, as low energy as you want. But if you have a staircase, if you can't get over that first step, you can't do it at all. And the mass gap is really talking about that same issue, just translated into how much mass energy the particle has. So there's the somewhat simpler way of thinking of this. And it's like I say, the whole situation is curious because this is a physics problem. This is not really a math problem. And yet, even David Gross agrees that there's a math component to this. That's interesting. Actual wording of the challenge. In fact, here's where we're getting to the terminology. So this is nice and compact, but it's all phrased very much in terms of the mathematics. So compact, simple gauge group. And of course, right there, you got to have to understand what gauge group, what is a gauge group, what is a group for many folks, what does compact mean? So there's a lot of math terminology you get into it. And it's a reasonable description from a math viewpoint. I mean, they are saying good things and appropriate things about what's required with this. But nonetheless, it also doesn't give you a whole lot of intuition unless you already understand that. It certainly gives you no idea about strategy, no idea of strategy at all. It's kind of like saying, like, well, we think there's a mathematical structure that has this property that no one has ever found in any mathematical structure that's ever existed, by the way. So that's a problem right there. He says nobody's done this before. So it is a challenge from the math viewpoint. But you also get into this issue is that because we just don't understand the math that we have well enough, or is it because the math we have doesn't really do this? And which is the point that David Gross brings up. So there's a long document written by Jaffe and Witten, Witten being the person mostly known for superstring theory, which is not the same thing as string theory. This is string theory, though. I mean, the work that I sometimes say that David Gross is one of three small set of real string theorists in the world who actually worked on the strings, which were the quarks with the ability to behave like rubber bands. That was the original string theory back in the 60s and early 70s. And then the name got borrowed to a very different concept at an enormously higher energy level. So they were the original string theorists. And that's where most people will be familiar with Witten from. And yeah, and this is just maybe I'm over being overly picky in this, but I don't like it when overcomplicated statements don't give you the gist of what's going on here. And I really think that somewhere in all of this literature that they had, someone should have stated this a little more straightforward. So maybe I'm being unfair on that. It's just I look at it and go like it. I know it took me a while to realize that's what they were saying. It took me quite a while to realize that's what they were saying, and that's why it irks me a little bit because I'm going like yeah, the people who wrote this had to know that. They had to know that. So help folks out a little bit and say uh, you know whether it does. Uh, as a math problem, you need to say that as a warning because it may not be true. Reality just might not decide to go the way you want it to. And that's another reason why you shouldn't always make math statements when you're not even sure of the result yet, because you may be trying to create a structure that corresponds to something that doesn't exist. So another grumpy quote from David Gross. Uh, Mathematics is an interesting intellectual sport, but you should not let it stand in the way of sensible information about physical processes. That's also called experimentation. You know, check it out, do the experiments. Don't always trust the mathematical predictions, no matter what they say. And of course, that's the very foundation of both special relativity and quantum mechanics. Is people said, oh, the math says this is the way it's going to work. And everybody tells me that it's 100% perfect and that's the way it's going to work. And it wasn't. People picked at the little mathematical fringes and said, no, this needs to break down a little bit. So another warning, and again, this one's a little unfair, but I'm, that's my own grumpiness coming through. It's like, couldn't you have said that just like right at the beginning? Because this is an area I'm not unfamiliar with myself, and yet I didn't realize until quite a ways into it that that was the simple version of the statement. This is definitely unfair, but I'm going to do it. If you actually read the Yang-Mills paper, it's kind of like a lot of early papers, inspirational papers that have a critical idea. The critical idea is what is important. And in that particular paper, their idea was that there were new forces inside the proton. That was brilliant. They deserve a Nobel Prize for it. That was the key insight. But the actual paper, was a little on the klutzy side. It did various things where they should have had a triplet. They had like a doublet. They used some terminology. It was kind of sloppy. The one that got me most, though, it is right in the abstract, and I have to quote this one just because this is where math models, if you get them too disconnected from the physics that originated them, you can start seeing things that if you really look back on it, you say like, should I really have said that? He said, no, maybe you shouldn't. And the one here is in the abstract, right up front, they said it's pointing out that the usual principle of invariance under isotopic spin rotation is not consistent with the concept of localized fields. That sounds profound, doesn't it? The trouble is isotopic spin rotation means converting a proton into a neutron or converting a neutron into a proton. Well, localized fields require that you not have an infinite range charge on your particle. So if you change a neutron into a proton, lo and behold, you are not going to have a localized field because you added a unit of electric charge. And that seems like an almost trivial statement. And Yet, to this day, in many of the notations for dealing with charge, charge is defined in the standard model of particle physics in this incredibly complicated way in which you have fractions of this added to that and all these other things. And some of that confusion stems all the way back to this paper because they didn't just make the simple observation. Of course, you're not going to have localized fields. You're adding charge. So instead, they looked at it and they kind of munged the issues together that there's a charge component to this and there's a non-charge component to it that really is another force. So again, this is unfair to pick on it because these guys figured this out, that there was something going on in there that was like electromagnetic charge, but wasn't. But they just kind of munged it together with a very strong component of electric charge also being in that. And the result is it does. The standard model truly does overcomplicate electric charge. Electric charge is a simpler concept, and you don't want to lose those simple concepts. The unitary nature, the conserved nature of electric charge is an important concept. Conventional approaches to winning this prize. Of course, with the, with all the warnings I already gave. So don't bet your house on it, even if you get it. Michael Atiyah, a good mathematician, gave a nice, very amiable talk and went over a number of things. I'm only touching a very small number of them. He gave a whole list of things you could explore to try to deal with this issue from a mathematical viewpoint. And he affirms that physicists seem to think this is true, although again, the wording is a little fuzzy. They don't never use the more explicit way of describing it, talking about rest mass of the gluon. But they also dive into all sorts of possible angles. One I notice is it has to do with infinite dimensional analysis because you're dealing with quantum field theory. I have an aversion to casual invocation of infinite dimensionality because I'm an information conservative. I think that information in the physical world has to have an actual representation as opposed to just claiming it's there literally without any physical proof for it being there. And as soon as you do that, you tie the information to matter and energy, which shouldn't be surprising because that's where we see, information is in matter and energy. But when you do infinite dimensional analysis, there you're running into the risk of confusing having a whole lot of atoms with the nature of the universe being inherently infinite dimensional. Those aren't the same statements. So he says this is the hardest of the clay student problems. Yep, I would not disagree with that. The other ones were not easy, but this one, because it dives into these physics issues, certainly has some things. Of the various resources you can find, if you look up online, I have to mention this one just because I thought it was a lot of fun. Professor Lorenzo Sadun, I don't know how to pronounce it, Sadun, University of Texas, gave a lecture on this about a year afterwards in 2001. And what I like about his lecture, if you're completely baffled by all this and you want a really quick idea of what all is involved, this one will do it because he literally just goes through the history of physics and how he manages to put this into an hour. I don't know. I his talk is good and he covers some nice things and he gets to some key points. I will warn you, this will not help you solve the Yang-Mills problem. This is too superficial in terms of doing it. But he did a great job of introducing people to the range of issues that are involved with this. So this is one of the resources they point to from the CMI site, and it's a nice one. He gave an interesting talk. But just look at that list. You've got Schroeder equations, you got de Broglie, I can never pronounce it right. He put in Klein-Gordon. I don't remember why he put in Klein-Gordon in there, but he has a nice coverage of relevant and some a little tangential, but items that you would need to understand. So it gives you some depth for the scale of the problem. There's a write-up that was done 5 years later. It's still referred to as kind of the canonical definition, for instance, of what the earlier problem definition that I gave is from this document, even though it did actually come quite a bit later. And this one dives you into a lot of the physics and the mathematics both. So this is a place where you can get into quite a bit of complexity to get more serious about that. It is from a highly math-oriented viewpoint, although it does bring up the physics also. And so that's a resource that you can go to, if nothing else, to get a full idea of some of the complexity of this problem. If there's anyone in the world who is close to solving this problem, who deserves to be given credit for solving this problem, et cetera, it's David Gross. His team, and I don't know who all works with him. I know it's not just him. He's got a team that's been working for 30 years on this problem, as he says there, doing calculations, looking at the actual data. And the interesting thing is they've come up with a fairly complicated, but also well-defined argument saying that based on the experiments we do, based on the various symmetries we see, based on what's going on with all of this, and there's a lot going on, that it does look like the gluons have mass. The way they state that is they say that if you had a glue ball, which is just something made out of nothing but gluons, which I don't believe have been verified to exist yet, that it would have mass. And so that was a way of saying it would have a rest mass of some sort. But they have done work that indicates that there's a gap. That is, that there is some kind of a mass issue. It may not be what we conventionally think of, but no, it is. It's a rest mass. It's saying that gluons have a rest mass. So they phrase that in terms of the mass gap. So he says, yes, it exists. There's an interesting spectrum of particles because as soon as you introduce mass, it's a stair step. It's no longer a ramp. Photons are on a ramp. Everything else, except maybe neutrinos, nobody knows on neutrinos. Neutrinos are a weird case. Neutrinos presumably are steps also, but yeah, they're so hard to measure. But the photons are definitely a ramp. Gravity is ramp-like in its behavior, if not quantum in its behavior. But everything else is stepped. So get two gamma rays together hard enough, which you can do. Gamma rays do occasionally interact with each other. You can get plink, you get a positron electron only after you've reached over the first energy step. That's your energy gap. So this is the gap that they're talking about. So until you get a certain amount of energy, you can't create the gluons, you can't get the interaction. So just marvelous work, and they've been at it for a long time. David Gross will never win the Yang-Mills Prize. He knows it. And this may be, I do think this might be a little bit of a factor in some of the grumpiness. You're like, I did all this, I figured this out, and and you get essentially no credit for it from the pure math perspective. But he also recognizes that something is needed. That our model. He's very blunt. He says, one of his analogies is physicists, we put a tightrope over the edge of a cliff and we walk out on it, blindfolded or something. So physicists take risks in terms of their modeling. And of course, mathematicians don't want to do that. They want to do the exact opposite. They want everything perfectly, based on axioms, axiomatic proofs. So he will not win the prize. One of his comments was that he couldn't even read. He read over some notes about his own lecture on trying to explain the idea of his asymptotic behavior of quarks. And he couldn't even understand the notes that the mathematicians wrote when he was trying to educate the mathematicians in that. So to say there was an incompatibility in the terminology would be an understatement. They just didn't use math the same way. And David Gross uses math. Oh, yes, he uses math very much, but it's not the type of proof type math that they tend to come from the other community. So there's an interesting little episode on that. Now, David Gross takes it in a different direction. He says, I think the problem here is that we don't have the right mathematical tools. So his point, instead of saying just assuming that everything in the Witten document is just is that's it, you don't need anything more, that's all you need. He says, no, no, we probably need to do something quite different. We don't know what it is, but yes, it would be nice to have better formality on these things. But none of this stuff, and David Gross repeatedly talks about it as being ugly and math. It's not useful math. It's neither useful nor pretty nor beautiful. Toy problems that go nowhere, small sets of things that you do enormous amount of work to get almost no results. So he's a pragmatist. He says, no, this doesn't really cut it. So the bottom line is just whatever they do, and they do need to do it. He agrees with that. Will probably be very different from anything that's been tried so far. If you're serious in your own pursuit, if you want to try to win the Yang Mills Prize, this is put a whole slide with big font just to say, look at David Gross's discussion of the Yang Mill theory. There is no resource you will find in the world that's going to give you a better understanding of the scope of the problem, the critical issues that of what we do know and what we don't know, of the research that they've been doing to figure out why it behaves this way, and ultimately to find the actual details of the behavior that you would then need to put into a mathematical model. If you look at the CMI materials, I'm sorry, they're compared to this, they're fluff, because they're all on this rather presumptuous statement that, oh yes, we've got this all under control, which is really a common thought back, especially around 2000, where everybody said, yes, the math is all perfect now. And where have we heard that? A century before, everybody said the classical math were all perfect, everything, just wrap up the details and that's it. So it's the same kind of a kind of an outlook here that, yeah, the math's all great. We just need to get the details down. And David Gross is saying, no, no, this is not doing it. These are these fuzzy little concepts that never go anywhere, or just take an enormous amount of work for almost no result. So take a look at his talk, and especially the later parts of it where he gets in more detail. You will find there's a lot of things you'd need to learn, and even if you're a physicist in these areas. But it's also a lot of good education about saying, what is known, what is not known, what methods have they used, where is the math proved useful, where is it proved not so useful. So great talk, can't recommend it enough. Part 3, okay. This is Terry talking. You know, if you watch any of my video, if you watch any of my talks, I take unconventional approaches. They're not complicated, they're just unconventional. So let's take a look at this. And I'll start with this. And this was my little advertising plug. This is such an incredibly simple point. There's nothing in this slide that is not verified out to gazoo. And yet, if you stop and think about it, it says something is wrong with how we casually use mathematics such as symmetry groups. And the point is, top slide shows what happens. You accelerate a spaceship to 0.866. I like that one because it gives you a Lorentz factor of 2. So you get half as much time as the clock whizzes by you. This was Einstein's idea. He said, get a clock and put clocks ahead of time. So I have a clock here on Earth, synchronize it with a clock on Saturn. You can do that. We do that all the time with satellites. This is not even new technology. Then, go to a star. That's a lot harder. But also, there are places in other galaxies, in the Andromeda galaxy, where they're essentially motionless relative to us. And that's the key criteria for saying, I am in the same time. I am in the same space, is that you're motionless relative to each other, not your distance. And it's an important criteria to recognize, because it does make a difference. Because you can find an enormous number of atomic, whatever kind of clocks, of systems that are relatively motionless. Relatively, I mean, obviously everything's whizzing around, but again, compared to the speed of light, relatively motionless. Out to nearby galaxies. So it's an absolutely enormous space. It's nice and mature. So, things aren't moving around. So we can actually say, yeah, a clock on Andromeda would have this time if it was set to this, because it's motionless relative to me. That's always the key criteria. Einstein went through an elaborate procedure. We would call it a program nowadays. They didn't have computers back then, but he actually gave the algorithm in his 1911 paper about how to do this. And he predicted the twin paradox by using exactly that method. He didn't do acceleration. He did clocks, synchronized clocks. So here's the problem is, and everyone's heard some version of this. We all just, it's just like a growing up thing for going through Einstein's relativity. You've got to hear this problem is the symmetry, the Poincare symmetries, the Lorentz symmetries, a subset of them, say that it should work in both directions. So that you have this idea that if you go from Beth's viewpoint, she's the twin in the ship, she should see everything else in the universe slowed down. And in fact, if she sees particles coming from outside the universe, that is exactly what she sees. No ambiguity, perfect resolution. A muon comes shooting the front of her ship. She will see it slow down and she will see it time dilated as it goes through her ship. The trouble is the last slide, because that only works for things inside of her ship that are inside of her little bailiwick, of her set of clocks, of her set of rulers, which are not compatible with the relatively moving clocks outside. And what she sees is she sees a compact, short, ship-size area in which Poincare symmetries fully apply, and everything outside is wrong. But it's not wrong in a weird, strange way. It's wrong in a simple Doppler way. It's not that different from a siren. You hear the higher frequency as it's heading towards you. You hear the lower frequency as it's going away. The same thing applies here. But light frequencies are also clocks. So when you see these clocks accelerated, and they get accelerated by a rather large factor, about twice that, the Lorentz factor, everything in front of you moves faster in time, not slower. That's your real resolution of the time paradox, is you only accelerated her. She's got the tiny domain. Everything else is still just sitting there following the old pattern. And the true symmetry is more complicated than just this simple idea that everything's Poincare symmetric. That doesn't work. That's not how the universe works, because those other clocks never got moved into your domain, and it would take them a long time for you to absorb them. And then you have delays and how you get them. You have to look at the beginnings. You have to look at the states. You can't just take it and say, oh, I only care about this instant and I'm going to ignore everything else. That doesn't work. Not if you want to get the actual answers. So this is a problem that goes back to the early papers, because I get into my other presentations, there's a tiny little math error of assuming that you can coincide the origins of Beth and Alex arbitrarily. And as soon as you do that, it creates a subtle math error that percolates through things, and it makes it very hard to figure out how this relationship works. If you abandon that, you can get it fixed, but you have to realize that, no, you can't make the origins come out the same. You have to do some manipulations, some changes to the accelerated system. Now, what has that got to do with Yang-Mills? It has a lot to do with it, because Yang-Mills and the formulation of problems like this are full of casual assumptions of symmetries without any constraints, without any limits, without any definition of when they started or when they ended, because, it's math. It doesn't end. No, yes, it does if you're applying it to the physical universe. So this is a kind of a key thought that just percolates through a lot of physics math. It's as long as you keep looking at the little piece that you like because it's so pretty, such as the Poincare symmetries inside of Beth's ship, you will not capture the fact that you can't do that. It does not work. It physically does not work, because you've ignored the action-reaction history, that when you accelerate systems, something else reacted the other way. And the one point that I always like to point out is that when you accelerate a system, you have energized that system. Energy conservation still counts, just because it's very much like the idea that if you don't know what the electric state that you're in, you could be inside of a sphere that's charged up to a very high voltage and you can't tell. Well, this is the same kind of thing. It doesn't mean that the energy is not real. It is, compared to the outside universe. It's just that you can't see it inside. A very, very similar principle applies to accelerated systems. You have your space-time definition inside of your system, but only inside of that tiny little area. And then everything outside of that can still see that energy is there and that you're in fact an energized system. So if you ignore things like that, you wind up with sloppy math. There's no other description for it. It's just sloppy because math needs to describe the full components of the system. You can't just take a little piece of it and say, I don't care about the rest. I want to make it, because then you just wind up generalizing nonsense that doesn't apply to the rest of the system. You'd lose the Doppler effects in the rest of the universe while you're focusing on the tiny effects in that tiny little area where you're at. Quantum mechanics, this is a pet peeve of mine. People talk about universal wave functions. Really? How do you do that? How do you do a wave function? First of all, I said, well, I get in the lab and I get an electron, I give it a certain state, or an atom a certain state, and I let it slowly diffuse out this way, and then I see a quantum wave function. Say, yeah, how did you start that? Did you start with a universal wave function? No, I started classically. I started here and did that. You can't ignore that. You can't ignore the fact that said my delocalized wave function started classically. Look at the history. History counts. So the idea of universal wave function always ignores the idea that, how did I get in the universe I'm in right now? Because it's classical. Right? It's full of information. It doesn't change, doesn't go backwards in time, except for very small exceptions. And you got to pay attention to stuff like that. So another grouch on the same issue. Einstein only used it before 1911, or up until 1911, clocks and rulers to measure space-time. He was adamant about that. He said you have to have actual physical objects to measure space and time. Turns out there's some good reasons for that, because the complexity of doing a cycle and the complexity of Pauli exclusion and all the other effects and the bonding effects that go into making a ruler are just not inherent in a vacuum. They're inherent in matter. So yeah, you can measure a distance across a vacuum after you have your ruler with all this extraordinary complexity built into it. But do you ever stop to think about it? Maybe the ruler is the one that's doing all the heavy lifting, because unless you recognize that the ruler has a major part in what you're measuring, you can wind up with abstractions that no longer are connected to what's going on with physical reality. So ignoring actual instruments, you lead. Oh, this is one of the last point. If you take space-time as being an infinite continuum all by itself, you've instantly made yourself compatible with quantum mechanics, because quantum mechanics is the physics of actual objects. So, in a sense, why is it surprising? If you ignore actual objects and just define a fabric that's infinitely precise, well, yeah, of course it's not quantum. How are you ever going to reconcile the two? Unless you acknowledge that the material components have a part in Beth's spaceship in defining space and time there, you're never going to get it to a point where you can have compatibility with general relativity. Another example, this is from a past one, but it's worth pointing out because this is relevant to particle physics. Mach's principle inadvertently assumes that there's instantaneous communication with the entire universe, because how you rotate has to be relative to something. And Mach exactly, he hit it, nailed it, and saying that that's got to be the average location of the universe as a whole, because he didn't believe this idea of an absolute space, and neither did Einstein, which is why Einstein liked what Mach said. But then you get into this other paradox and say, well, then how do I know instantaneously that this is what the universe says is rotation and this is not? And the answer to this is much more simple and much more local, and heavily involves remembering history. Do not forget the past. Every time you get a rotation, you counter-rotate something else. This is called angular momentum conservation, not a difficult thing. So you can create arbitrarily large amounts of angular momentum, but guess what? When you add them all together, they all go back to zero. And that zero represents that localized idea of the Mach memory of how the whole universe is working. So what it is, you're just breaking it all down into little tiny pieces. So why is this relevant to particle physics? Because particles have spin. And every time you say that a particle has half spin, it has whole spin, it has some function of spin, you have connected that particle as an isolated unit to the entire structure of the universe relative to that original definition. So it's like you're just grabbing hold of a little bit of a memory of that outside universe and using that to define it. So you can't talk about spin as being just totally isolated from the rest of the universe any more than you can spinning yourself around in a circle. There's a connection there. And without that connection, it's going to be hard to say how these things all work together. It also means that you can take bits of the universe, such as spin, and take them down to incredibly small levels, such as particles. And then at that point, the physics is dependent on that ability to dissect the symmetries, to break them down into these smaller pieces. Review slide is for just one from another one, but just to repeat it in case you have not seen me talk about this before. The idea that I really like to suggest is just, it's very data driven. It's sparse information physics, I've already talked about it, only matter and can create space and time. Now you can say, oh, but no, it's matter, space-time is a fabric all by itself. Yeah, well, you can conceive of that, but you can't actually test that. And I don't care which version you come up with, how you do it, the vacuum is a vacuum, there's nothing there. You can't measure something that's not there. So you say, well, there's a Casimir effect. The Casimir effect only exists when you have intense amounts of matter and energy in the vicinity. You can't do it, you can't do it in an actual vacuum. So empty space is immediately compatible with special relativity because everybody looks at the same empty spot and they see nothing because there's nothing there. The moment you go to Planck foams, and this is not a popular view, but it's also just the arguments for why this is true are not even complicated. If you try to create a Planck foam, you instantly have an observer perspective problem because different observers will see that foam at different energies. And you can't do that. You can't call that special relativistic space, vacuum, because you've just tied it to one particular frame, which will be the minimum energy frame for the Planck foam. So to me, it's just remarkable that we have these concepts and we don't realize how much we've localized them to a particular inertial frame, because we create the space and time in that frame, and then it just becomes so intuitive to us that we just don't stop and think that, oh yeah, I just locked it into one frame, mine. And you can't do that when you're talking about the broader relationships in the universe, or there's relationships down at the particle level. So nice advantages of a sparse information physics. You get away from a lot of these weird cutoff issues that pop up. The one I always point to is that gamma rays can be as energetic as you want them to. There's no limit. They can be so energetic that they would fall apart if the universe was made out of superstrings, because the superstrings are too big and clunky. So the universe is subtler than that, and it goes in more of a kind of a funding type structure. How much are you going to give me? I'll give you as much precision as you want, as long as you pay for it. So it gives a very different perspective on issues like quantum foam. Hilbert paradox. I'm going to bring this up because I've just ragged on some of the issues about how these mathematical models work. Hilbert wanted to see mathematical treatment of the axioms of physics. The point I would make in this is that you can't do that if you expand every one of your axioms to be pre-existent, Platonic, however you want to phrase it. In terms of physics, if you want to create a Platonic world, you can. You can't calculate it because everything would cost you an infinite amount of energy to calculate it, but you can certainly conceive of it. But if you're talking about physics, actual physics, you can't do that. Symmetry groups such as Poincare, the example I just gave, the reason why the twin paradox is not a paradox is because the Poincare symmetries were localized. They don't belong to the entire universe. They only belong to that spaceship. You have to physically restructure the spaceship, literally compress it, literally change the clocks in order to get it into that new Poincare group. So You didn't do that to the rest of the universe. So if your symmetry math does not respect that, you're not going to get right answers. And any kind of infinite symmetry thinking tends to take you away from that reality. Points are real, independent of the coordinate frame. This is not true. Points are dependent on the concept of a XYZ coordinate system that belongs to a particular inertial frame. As soon as you start breaking that, if you have a small object, it starts looking compressed. You have different changes to it. It no longer fits the true definition of what a point is. So even the concept of a point, you have to be careful. Continuums. I talked about this in my last presentation, the idea that back in the 1800s, they decided they had this all wrapped up, that everything is a continuum because you can always define a way to cut something, Dedekind cut that goes this way, Dedekind cut, I'm probably pronouncing that wrong, that goes that way. And algorithmically, that's fine. But what it ignores is, once again, you have to execute that algorithm you just created to infinity in order to make even one of those cuts. And again, people just ignore this, say, well, but it's there. Well, it's there in some virtual sense, but if you're talking about physics, you always have a limit of some type about how much detail you can actually create. So my suggestion is that the Hilbert paradox is, I like what Hilbert is trying to do with this, but many of the concepts, especially on infinite differentiability, infinite smoothness, have to be abandoned, and you have to flip it upside down and say these are emergent properties. Now there's some heresy. The idea that differentiability is an emergent property of large collections of classical matter. And yet, if you look at the actual physics, that's the way it works. The more matter you have, if you're in condensed matter physics, these equations can be just incredibly smooth and it works fantastically. But when you start talking about the fabric of the universe in terms of the individual particles, best be careful, because at that point, strange things start to happen. Things like quantum mechanics, where things become uncertain because they no longer have the definition needed. Yang-Mills generalization of Maxwell. There's an interesting statement by Michael Atiyah. The Yang-Mills equations are, very crudely speaking, a matrix version of Maxwell's equations. I thought that was a very nice summary they gave on that point. I think that really got to the heart of the insight that Yang-Mills had. Was that you are doing another version of Maxwell's, which is one of the best. It's so sad that Maxwell died young. What an amazing mind! Absolutely, people should look at Maxwell's work sometimes. This is a mind that he figured out the speed of light without using mechanical models. He figured out light was a form of electromagnetic radiation using mechanical models. He didn't even have differential equations yet. So just an amazing mind, and well worth reading some of his materials. So Maxwell's equations. So that was the insight. Now, I just want to make a point, and here's where I'm going to go in a little bit of repetition mode from things I've shown before, but I want to point out a connection here. There are other ways to generalize Maxwell's equation. You don't have to go straight diving into the matrices, which you can inadvertently add a lot of noise to it. But you want to look for ways in which you might have a simpler thing. And one of the first ones, it always intrigues me that goes all the way back to 1979, is a fellow named Sheldon Glashow, well known, of course, for the standard model, had a little mnemonic, and this is the actual figure of the mnemonic, that he showed that if you lump matter and antimatter together, you just get this delightfully simple cube that shows you what the charge relationships are between electric and color charges in the particle types. And he recommended it as a mnemonic, something that you could look at. But everybody was totally into the whole standard model was emerging that time with a different set of symmetries that didn't look like this. And not too surprisingly, he just I'm sure he and some of the others who looked at that said, maybe we ought to explore that more. But, they were having good luck with the strategy they were using. They're having good luck with the symmetry groups they were using. So this just kind of got skipped over in history. It didn't go very far. I think that's unfortunate because there's actually two cubes. When you put them together, you get all of the particles in one fermion family, one family of matter. And you also get a number of rather remarkable symmetries in terms of how charges work with these things. So this is what the double cube model looks like. And the charges, what's interesting about the charges is in terms of actual particles. I really want to emphasize this. In terms of actual particles that we see, as opposed to hypothetical particles, hypothetical math, hypothetical fractions of charges, what we actually see are vectors that are combinations of color charge and electric charge. And when you add those different combinations together, this is why protons have the same charge as electrons. You add those together, the colors cancel out, but you don't wind up with zero. This is the part that they don't teach well in this. And I've seen many textbooks that make this mistake. They don't emphasize that for every particle ever observed in the universe, color is always associated with some electric charge. And if you don't recognize that that forms a vector, you don't get this cube and you don't get this relationship between the electric and the color charges. Why is that important? Because once you have a set, really just set of three axes, it's a three-dimensional space. You get this three-dimensional axes of charge, and these charges are neither exactly color or exactly electric. They're the composite charges that are a mixture of the actual mixture that we see on real particles form these vectors. And those vectors form a nice three-dimensional space. And guess where Maxwell's displacement is on this space? It's going straight up. So I'll go back on that, but see that dark vector there? That's Maxwell's. That's the electric vector going straight up. The point this gets at is that all of these things can be grouped into a space in which the electric charge, same electric charge that is the isotopic spin charge, you have this relationship between these two cubes, and it forms a four-dimensional cube, because it's the easiest way to make a four-dimensional cube is take two cubes and then just connect all the vertices. It's actually very easy. And that's what you get with this. And there are names for those pieces. It's an SU2 symmetry. This is a generation 1 fermions. You've got two more families. The T sub 3 weak isospin is a property. I said the terminology gets a little interesting, but that's what these bridges are. And all of your fermions become become rotations across those bridges. So if you rotate it one way, up here you get the positron. If you rotate it the other way, you get a neutrino, an antineutrino. So each one of these different, I'm pointing with my finger, which I'm not sure if that helps, but each one of these is one of those isotopic rotations. So, it's no longer at the proton-neutron level. In this case, you're conserving charge, you're paying attention to charge, but the relationship's still there. These are those same rotations, those same little symmetries that first inspired the Yang-Mills concept. But look how much smoother this is. This is a tesseract. It's a four-dimensional cube. This is a nice, smooth structure, a nice symmetric geometric structure on which you can start asking questions like, what are some of the relations? And I think I skipped putting one slide. I was going to show that there's a set, the gluons just become relationships between these different levels. And there's this marvelous little, I've got it some of my earlier presentations, but there's this marvelous relationship between these fermions and the vibrating, oscillating possibilities that we define as photons and as gluons. So it ties them all together much more closely. You don't have the distinction that you have between the color charge and the electric charge that is traditional. What the grand unification comes in a very natural fashion. So that's important. Now, here's a hypothesis I'm going to put out, and I've mentioned this before, but it's a hypothesis I've been using, oh gosh, for a long time now, and it's served me well in terms of analysis. Time and charge are linked. And in particular, time as we know it as large-scale time is the vertical axis of those cubes, the vertical diagonal of those cubes. So why? Because the other ones seem to have a different definition of time. The quarks literally are kind of going off in their own definition and saying, I like time to be this way, I like time to be that way, into this three space. Now, what Maxwell saw was he said, well, at the level I'm looking at, of course, he didn't know about any of this stuff. Says, I only see these displacements going up and going down. And he was fascinated by that. He said, I don't know what these things are, but they seem to work very well. They have infinite range in terms of how they apply. And this is where you get that kind of a time relationship, that if you have that perfect vertical structure, suddenly you're compatible with space and time in a special way. You have this little linkage. Protons get the same idea, but they get it in a more complicated fashion. And when you go inside the proton, it's not clear at all. The electrons have a different way of combining these things, so they all show up just as a single charge at the level that we look at it. But these times and charges are closely linked to our concepts of space and time. And they introduce the rotations, the spins that are necessary to define little tiny clocks. So surprise, surprise, you have to have clocks at every level, and that includes fundamental particles, which is one of the reasons why they have spin. So the answer from this kind of analysis is that any particle that goes outside the central axis has mass. And you wind up hitting the same idea of gluon mass because of the relationship. And again, I'm sorry I missed that one slide, because I do have a lovely little slide about the gluons and showing how they relate to the structure. It is in some of my previous slides, previous presentations, I think. So, in summary, you're interested in this prize, pay attention to David Gross. Not so much to CMI. The CMI has some good reference materials, but if you really want to get into the problem, I mean, just know where this thing is working and where the physics is and why the physics are interesting and what needs to be modeled. Look at what David Gross and his people are doing. That's where you're going to get some really good stuff. And a serious, I mean, obviously there's a lot of work in that, but that's where you get a serious path to doing something significant on that. Work to solve the problem, not the prize. The prize, yeah, maybe it'll materialize. If you can, if you can actually do this, though, there is a good chance you get a Nobel Prize. So there's your alternative. If you can do the kind of restructuring of mathematics that David Gross recommended, and it's predictive, that's the way you can get a Nobel Prize. So the CMI prize would be kind of irrelevant at that point. My own bias is that using bottom-up approaches to reality, starting with mass and energy, just give you a lot of what? They give you new nuances and complexity and combinatorial possibilities with symmetries that you don't get if you just use these bland global symmetries that are just assumed to apply everywhere. So, example, Minkowski space. I was reading through some of these materials and said, well, if we go into Minkowski space. Now, for me, that instantly is a flag and say, oh, so you're using the Minkowski transformations to go into a newly created space-time instance of some smaller size, which is a very different statement from just saying that I transform everything and the entire universe comes into this new viewpoint. That's the kind of precision, though, that you can start analyzing things in more detail. You say that, well, I can create a Minkowski space instance in this case, or in other cases I cannot. The Minkowski space is essentially a transformation for how you flip yourself from the outside viewpoint back into that ship. So suddenly you become Beth. That's the Minkowski transformations. But everything beyond that within that ship, you're better off with the Euclidean. And it's interesting too that Yang-Mills problem is stated in terms of Euclidean spaces. I like that, because the best analysis you can get on special relativity problems is to acknowledge the Euclidean viewpoint of the majority observer, who's the one who's setting everything up. And everything is an excitation within that viewpoint. That's where you get some power in terms of breaking it apart. Infinities are bad. Math noise from sloppy assumptions, such as the casual assumption innocently done, but Yang and Mills, where they assume that, they essentially separated charge from the idea of the fields. And yeah, you want to pay attention to the actual material, what's going on. Don't assume that you can take an abstraction, just skip over that part, and that you're going to come up with a good abstraction. You won't. You'll come up with a lousy abstraction. You'll come up with a lot of noise. You'll come up with incredibly convoluted ways to do simple things. So you don't want to do that. Infinities are okay. Yeah, infinities are bad. The universe does not like infinities. The Greeks did not like infinities. Um, they're interesting, and there's the whole alpha series is fascinating. I love going through that. I remember even in grade school, I used to think about infinities. It was just such an interesting topic. But if you're talking physics, yeah, you really want to be careful when you start invoking infinities. And that includes Hilbert spaces with infinite dimensions, because as soon as you go in the Hilbert space, you have these infinite dimensions, infinite information, infinite varieties, and the actual physics is always constrained by the fact that there's no universal wave function that we can detect experimentally. Yeah, you can define it if you want to, but we don't detect one. We only see small instances of quantum wave functions that have finite lifetimes. Uh, this final point, this is a simple point, but I'll be adamant about this. There's a huge search for grand unified theory, unified theory, grand unified theory. Yeah, grand unified theory was the one that was supposed to combine electric and color into one thing. Uh, I have an extremely simple assertion on that, which is that they never split. And the reason there was so much trouble finding the group that would represent both electric and color is because they never split. And had Glasgow and company followed up on that little cube they wrote and looked at the implications and looked at the mathematical implications of that cube in terms of structuring the overall model of the models, I think they would have come up with something that was less confusing and used fewer symmetry groups, because the electric and color would always have been just vectors that Maxwell could only see the result, and that they were always there. So you had the three color vectors. They combine to give the electric vector. In the electron, they do it invisibly, which is fascinating. In the proton, it's much more explicit. But in any case, there's a simple three-space there, a Euclidean three-space of charge that explains a whole lot of stuff, including potentially why you have mass on gluons. And with that, I will wrap it up.
Yes, thanks very much for this very insightful lecture. It's quite interesting. Learned quite a lot from your lectures. I've got some query. It's more philosophical, perhaps. Is this question about mathematics and physics? They are clearly two different disciplines. However, there is some connections between them, and this is well understood. My problem is I just wonder whether mathematics could exist independently from physics, whereas the reverse, the physics perhaps could not exist without mathematics. I wonder what your views on this question. But my view is that the physics requires quantification, characterization, and expressibility, and which for that mathematics is essential, whereas mathematics perhaps may not require physics.
Okay. I would answer that in two parts. That something underneath at a deeper level is following some extremely precise rules. Conservation rules are the ones I tend to point at, that conservation rules are deeply fundamental. The idea of pair production, that there's some kind of a math that is probably more discrete than we realize, but it's not. I'm not talking about a lattice universe at all. I'm talking about something where entities come into existence in pairs. At that level, describing that as being a math first issue, I think is has a lot of appropriateness to it. That there's some kind of existence that is beyond the existence of the matter, because the matter comes from somewhere, and whatever came from was the level of complexity of matter and of classical space-time argues that there are simpler levels of complexity below that. So I would certainly not dispute the idea that there's a structure and a consistency that is better described as math at a deep enough level. My problem is that I think we grabbed way, way too high of a level of the mathematical abstraction and declared it to be sacred. And that's what I think is dangerous, is whenever we talk about continuums, we are instantly talking about classical mathematical approximations created by extraordinary numbers of atoms that have the ability to isolate themselves in terms of how to interact with each other. And that's not the same thing as saying that space just exists. It's saying that these are remarkable and highly complex relationships between particles that present themselves in these ways that we think of as high-level math. So what I would argue is that we need to break down many of our assumptions. And I talked about this in my talk last month. Space always has a duality to it. And that's not new. A lot of physics and mathematics likes the idea of these dualities. I would certainly agree with that. But the idea that separation itself always has a wave duality, a Fourier transform duality, and everything we see, that's a reflection of some deeper physics. But I would not focus on just saying just the higher level repercussions of that, the fact that it creates a space for us where it's easy to separate objects. I think those are the more superficial symptoms, though, and marvelous instantiations of it, because it allows us to have things like objects and separation and space and particles. Without all those, we wouldn't be here talking about this. More than anything else, it enables the idea of information. So I think a deep mathematical basis, but I just think we're focusing on the wrong parts, and that if we look more bottom up and say, well, yeah, that looks like a continuum, but I know that's just, classical matter speaking to me. That's my classical mind speaking to me, where atoms are so small that we think they're not there. And of course they are there, and they get quantum. And when you get to that quantum limit, that's where you're starting to break down that consistency. So deep math, maybe we should be a little less quick to grab the things that seem so familiar to us.
Yeah, thank you. Thanks so much.
Any other questions?
Hey, Terry.
Hey, Ron.
This might be somewhat of a naive question, but early in your presentation, you referred to particles having characteristics that you referred to as color, and you said that was very apropos, so to speak, because these particles mix in the same way that colors do.
Yes.
Were you making reference to, applied physics color model, like,
What these
or
are,
something else?
these are the color charges of standard model of particle physics. When you have a proton or a neutron, they have three quarks inside, and each of those quarks has a charge. And for various reasons, they started calling those charges color charges. And surprise, surprise, they call them red, green, and blue. They also have anticolors. So the color in that reference has no connection at all with photon colors. The reason it's appropriate is because when you combine red, yellow, red, green, blue, you get white. You get a colorless result. And this is what they noticed on the behavior of protons and neutrons, is that when you put three quarks together, and each one has a different color, red, green, and blue, the result is colorless or white. So it just that's the analogy. And it actually turns out to be a quite useful analogy. If you, on the slide that I had, you notice I color coded everything for just that reason, because it works. And it's one of the reasons why they use that terminology in the first place. So no connection with regular colors.
Okay, but is there still an analogy of just mixing two particles and getting something that's similar to a third one, or?
Yes. Yeah,
Okay.
because what happens is you get mixes of colors that are always confined. Color does not pervade the universe as a whole. It's strong confinement, which is what David Gross's work was about. But the colors are strongly confined. But within those, yeah, you get a lot of complexity where you do have color mixing, you have colors canceling each other. Quarks, they exchange gluons. The gluons actually have mixes of colors. They have one anti-color and one positive color. So yeah, it's a little paint palette there that goes on inside of a proton or a neutron.
That's fascinating. Thanks, Terry.
You're welcome.
Hi, Terry. I'm going back to the question related to colors, and I'm wondering, is that the same principle with computers? I know in computers we use a lot of colors, mainly in the web design, videos, image processing. So are they also related to charges?
The colors, the color scheme, the particle physics really borrowed what was already known in the technical community that makes like color screens, because each one of our color screens has these days has a red dot, green dot, blue dot. You can see them if you put a drop of water on your screen. You can see the small dots where they do that. And all the images we're looking at right now are indeed composed in that fashion. So RGB is one of the, to me it was funny. There's a license plate I saw once on a black van in front of me. It said RGB 000, and I looked at it and said, oh, that RGB 000 means black. So it was a black van. So yeah, so it was yeah. So it's the physics borrowed the common terminology in that, but it was handy. It was handy.
Thank you.
Anyone else?
Sure. One of the stories they tell about quark dynamics is that if you take two quarks and you pull them apart, this will require so much energy
Yes.
that it will eventually turn into a quark and an antiquark, so you'll now have two particles. And this is similar in some ways to the way magnets work. You cannot create a magnetic dipole by just sawing a bar magnet in half. Is this something where we have a similarity here, that these things are in some sense dipoles?
There is a similarity there. The magnets are a dipole, so the main difference would be that in the case of quarks, it's a six pole system. You have this variety of charges you can do. When you give the example, which is exactly correct, they pull two quarks apart from each other. It's a bungee cord. It behaves exactly like a bungee cord, and eventually you store up so much energy it snaps, and then you wind up producing another pion pair. You produce another pair of quarks, quark and an antiquark. And magnets, I'm trying, something keeps tickling my memory that I've seen an analogy about the magnetic force and that similarity that you're talking about. But you bring up an interesting point, because it is like that. You cannot at long distances separate the two. The interesting difference in quarks is they do have specific charges. So like electrons and the protons, they have specific charges that are tied to some localized point in space. And the magnets don't have that. They have a generalized field that you can't break without creating, another set of the same kind of things. But it's an interesting analogy. In fact, I have to think about that a little bit. That's an interesting point. Anyone else? Hey, Helen?
I know, sorry, Terry, it's just no one else wants to ask. I got too many questions. I want to learn a lot so much about physics. But question, you mentioned about vacuum, and I'm really intrigued. And also you mentioned that, we're trying to avoid dealing with the infinities, like infinities, like purely theoretical concepts. But I wonder the nature of vacuum itself, and in quantum physics, the energy, the fluctuation energy within the vacuum, that level of fluctuation energy is theoretically infinite.
Yes.
So therefore, why we avoiding, going on theories which accepts and deals with infinities?
This is actually when I mentioned the point about Planck foams, this is actually something where I absolutely diverge with most physicists on this point. Planck foam is considered just a given these days. And one of the reasons it's considered a given is the Casimir effect. But if you look at the Casimir effect in general, it's so much better modeled as the last remnant of bonding energy. And that's not just me, that's Casimir who said that. That was one of the last statements he made. It's kind of almost like a little, I think it was like he had to say that in his later years because I think he thought it for decades, but he didn't want to say it out loud because he was afraid it was going to offend everybody. But Casimir pointed out that the Casimir effect is based entirely on bonding energy. So you take two pieces of metal, you split them apart. At first they attract, and then it gets thinner, thinner, thinner as you go on out. And that was his explanation for the Casimir effect. And yet, from that effect, Bohr extended the idea of the vacuum frenzy, and Wheeler especially, to everything. They said, well, that's proof. That's proof. It's all infinite uncertainty at that level and infinite complexity and infinite everything. And it all just averages out. Now, that is the worst predictive model in all of quantum physics, because that's the same model that predicts that the universe will collapse instantaneously or explode instantaneously because of infinite mass density. So the theory is there, but there are so many ways that you can, if you want to try and make the effort, can get around that by simply invoking Casimir's rule. That is, the energy which is available for your wave oscillations is never anything more than the bonding energy that was provided. That puts a cap on all of these calculations that produce these infinite densities. Feynman did not like that idea. And this is ironic because Feynman got a Nobel Prize for creating that concept. So, he was the one who came up with the Feynman diagrams that produce these almost, they're not quite infinite, but almost infinite energies at very small scales. And yet Feynman, this is where he got a laugh talking about himself and say, this sounds wrong. It's probably more like a game of checkers. And he was expressing a point. He couldn't figure out a way to get around it, but he knew it didn't sound right. And he was saying like this doesn't feel right. So absolutely the standard model you will see in almost every physics talk is infinite energy, infinite density, Planck foam, just roaring crazy stuff going on down there. And I don't want to. It's you can look back at some of my previous presentations, but there are just so many reasons to say that's not actually what we see in terms of the material behavior. Just as I mentioned with Casimir's rule, Casimir's rule being that you'll see all this stuff, but it will never be funded by anything more than what you put into it. And that's a very different view of space-time. That says that space is mostly empty, maybe some very, very weak fields, and that you will never get spontaneous emergence outside of that part of the vacuum. Now, within the matter, things get a lot more interesting. So, you know, something interesting is going on with this. And if vacuums couldn't do anything, I don't think we'd be here. But the Planck foam concept, there's a lot of ways to dispense with that if you want to put in the effort. But who wants to put in the effort? It's even as I'm saying it, like you've got an entire how many decades of calculation of working models, and that's important point. These are not models except for the vacuum density thing that doesn't work, but these models work very well at small scales in small locations and extremely predictive for like electrons. You know, that's how Feynman got his PhD. So these are real models, they work, but we need to pay more attention to the limits. And one of those limits we need to pay attention to is the energy funding issue about where does the model stop and where does the model just cease to describe pair formation that's being driven by available energy. And I think actually there could be just some really interesting research in that if folks want to get into it.
Thank you.
You're welcome.
I saw a question from Zara. The mass of up or down quarks is 3 MeV, but when they form proton or neutron, the mass shoots to 937 MeV.
Yes.
Why is that?
That is exactly what Dave Gross is covering in his work. And Dave Gross, his perspective, and this has gotten into some of the physics community, is that most of the mass of the proton, this is his perspective, is that most of the mass of a proton and neutron is from gluons having mass. And that actually this is where that complexity is coming from. Because yes, the masses, just like the electron, the masses of the quarks are quite low. And those estimates are done using the Higgs mechanism, which is the same one that's got so much attention a few years back. But that's a different mechanism. And that's the core of Dave Gross's work for the last few years, is this idea that those gluons don't just have energy, but they have some minimum mass to them. And you add that all together and you wind up getting protons and neutrons. And apparently he's got some pretty good calculations, as he said, not rigorous, not super rigorous, but he's got some pretty good calculations about why that is. So yeah, that's a good question. I say that's at the heart of this whole thing, is the mass limit. So again, I would phrase it in terms of gluons have mass, but that is the very same mass function that they were talking about in the Yang-Mills challenge. Anyone else?
So the title was How to Win $1 Million?
I'm sorry, say that again.
Why did you title this presentation How to Win $1 Million?
Because when I first got into it, I sincerely thought this prize was a good possibility. And then the more I got into it, I didn't retitle the slide, but I was going like, why you probably would have a very hard time winning $1 million would be a better title for it. Because if Dave Gross can't get it, I don't see how any of us can get it. Because he's, which may be why he's a little grumpy. But my point, there's still a point there, which is this: if you can solve this, forget about the CMI. You'll get a Nobel Prize. Completely in complete seriousness. If you can solve this problem, just don't worry about the CMI stuff. This is an area that needs math modeling, exactly as David Gross said. It is an area that requires some new thinking, some innovative approaches. So taken from that perspective, someone could develop some entirely new set of models that come out and say, oh, yeah, here's what's really going on. At that point, you really do start getting Hilbert's idea of an axiomatic, a more axiomatic version of physics. That's still a good goal. I mean, there's nothing wrong with that goal of axiomatic physics, because there's a lot of regularity going on down there. So, yeah, I would defer it and say that your more likely opportunity for getting the $1 million prize would be to get a Nobel Prize, which may or may not be that much money, but this is good. There's a good challenge in there, and there are rewards for succeeding that challenge. And who knows, if people consolidate around it, and you have that, you should get the prize from CMI, and you might. But it's just so many mathematicians you'd have to convince to whatever your new method was, and that would be a heavy haul. That'd be a heavy haul. The Nobel laureate committee would be more likely to be responsive, because if they see a model that predicts new things and says, "Oh, here's what's going on here," that would get attention.
Thank you so much.
You're welcome. I'm not, I can't, it's hard for me to see the chat. Is there anything from any chat questions or anything I'm missing?
I saw a comment from Peter. Thank you so much for the informative and interesting and entertaining talk. Come for math, stay for the physics. Come for the $1 million, stay for the contribution to science. I think the phrase you were looking for was unified field theory.
Could be, could be. Thank you. Thank you very much. Much appreciated. Ellen, shall we be putting a wrap here? Anybody else?
Yeah,
Terry,
anyone?
just a small detail. I forgot to ask this question. You know, you mostly talk about the Young Mills challenge. I wonder, for this prize, is given the challenge, or can it be any of the 23 mathematical challenges out there?
They only list a small number. It's just seven prizes total. The 23 prizes, oh, I don't remember. I remember there's a list of 23 challenges, but that's a different, I don't remember who put that out. That's a different list. So you can follow the reference materials on
So they offer only 7
only 7.
for
One of which is
the prize, yeah.
And of course, the one that's getting attention right now is, oh, somebody help me, the Navier-Stokes. Navier-Stokes is a lot of attention because they've used machine assistance on that one. And I have very mixed views about that, because if they're using traditional AI, by traditional I mean non-chatbot AI, I think they could be doing something really good there, just like they did with, like, seeing the structure of a black hole, human genome. There's some fantastic things you can do with a more traditional approach of AI, including some aspects of the LLM technology. But if they're using LLM heavily on a proof, I wouldn't trust it further than I could spit. Because,
and what about an AI? If AI comes out with a solution,
if it's an LLM AI, it's not a solution. It's nonsense. You can't do 2 paragraphs with a chat bot without getting errors. And the canary in the mine is if you look at what's happening to lawyers, because lawyers have a solid reference base that they must adhere to. And so many lawyers are getting skewered by using LLM, and they see this pretty looking output and they think it's good. And it's not. It's never good. It's never, this is not a sentient thing. This is a database. LLMs are databases. They are not sentient. Because they have content addressability. If you ask them a question for an argument, they'll pull up the argument that someone else gave to that question, but they don't understand the answer they just gave. And this is so important for people to realize that, especially in areas like security. Debbie Reynolds on her security podcast, I have a security podcast interview with her coming up in 3 days on the 14th. So I get into some of that about the dangers, especially in security, of trusting the large language model, which is a statistical database structure for doing things like security. I know it talks good and it does impressive outputs, and it has augmentation. Like if you want to ask it to redo a picture for you, that's fantastic. If you want to have it do something, that's retrofitting something, that's good. Checking order for grammar messages. But if you try to compose with it, you're using tea leaves to forecast your life. It's a very dangerous thing. That's a little bit tangential, but yeah, that's so in 3 days, that podcast should be coming out. That'll be fun.
Yeah, thank you.
Yeah, yes, going back, I have a question, going back to LLM. So, you say that if you want to produce something, LLM are very dangerous. Can you explain more about that? I want to be
Yeah.
curious.
And it also, the statement I made, and this has been an incredibly frustrating thing for me, because I helped get funding into this area. I helped. I'm still active in the AI community. So the large language models are exactly what they say. They're statistical models of large sets of language, and that is not the same thing as sentience. It just isn't. It's saying, like, painting a picture of a tree is the same thing as a tree. No, it's not. It doesn't do photosynthesis. And if you say that you paint a picture of somebody's conversations, it's going to look a lot like those conversations, but just like that painting of a tree, it doesn't know how to grow. It doesn't know how to produce sugars. It doesn't know how to sustain itself. None of that's there. And people have tried different techniques. Oh my gosh. We've had, again, this is something where I'm involved directly with a lot of little research, the various size research groups. It doesn't, bless everybody's heart. Folks have tried for decades, for years, to make these things more self-guarding, self-checking, the idea was that you put enough common sense into one that eventually the common sense will take over and it'll just take off. It never happened. And the models now are just actually making it worse. They're actually a fantastic proof that it doesn't happen. Quite the opposite. You can't create sentient thinking out of a statistical model. All you can do is recover people's expertise with varying degrees of reliability. One of the most dangerous things about an LLM is you get an expert in front of it, and that LLM's been trained on that expert, like say a professor who wrote a textbook, and the professor will ask it questions, and the professor will conclude, my gosh, it learned everything. It knows everything I have and quoted it back to me perfectly. And you see these ads for things like that, where they say, oh, the LLM has now reached this level because this expert did that. This is all an illusion, because it only gives the perfect answers to the person who already knows the answers. Anybody else is going to get varying degrees of crap until it turns into total chaos. That's the difference between a database and an actual intelligence. It's giving that professor what he wanted because he asked exactly the right question. He addressed his content addressability. He gave exactly the right query to index his own information and get it back. So this produces, but it's just such an illusion, because you see experts saying, oh my gosh, I tried it and it's so good. I think I saw Terrence Towell once was talking about how much progress it made. Dawkins said something about it. That's the illusion. You get an expert in front of it, and it's trained on that expert, and lo and behold, it answers what the expert wants to hear. But it doesn't mean that you can use it to plan your life. It doesn't mean that you can use it to write a novel, because the best it can do is just steal somebody else's novel. Other than that, it just starts falling apart very quickly. So you want to be careful at LLMs. They're not. More and more I refuse to call them an AI technology. They're a database technology. There are many forms of real AI and some good DeepMind. Some of the stuff they've done is just amazing. But you want to be careful with these things.
So what do you say about hallucination? If you are saying is true. So what do you say about hallucination?
Hallucinations are built in literally from the bit storage level in transformer technology. The first thing that a transformer does when you put in a new bit of information is it shreds it into thousands of pieces and adds those thousands of pieces as weights to thousands of different nodes, to these little word pairs. I like to call them, well, they're just word pairs. That's how it stores data. You have this one word and says, what's the probability? Marco Polo pairs is what I tend to call them sometimes. You say Marco, what's the chance I'm going to say Polo? And then you attach a fixed probability to that. That's a terrible way to store facts because the probabilities are just that. They're just probabilities. There's no sentience behind it. It's just a fixed number. And you can use it holographically to store the data. It's literally like holography, but you can't preserve it. So when the first thing you do is you destroy your fact, of course you're going to get hallucinations. There's no other possibility because the data's gone. The pristine image of it is gone in these systems. And everything else is probabilities. And so people think that the hallucination thing will get fixed. It's not fixable, not with this technology. You have to go to a different technology that actually understands what it's doing. And you don't want to use the LM as a base underneath it.
No,
So,
what I was trying to ask is that don't you think that hallucinations is part of LLM intelligence, since they can produce things by themselves, like they can synthesize things by themselves without copying what someone's has already given them.
they can, this is the idea of the trouble is that cognition is a matter of reduction and removal. And this is an incredibly important difference. An LLM is a master of generative, of producing combinations, of producing every possible combination. Actual intelligence does the exact opposite. It says that of all this crap that's coming out, what is the part that I really truly need to focus on? And this is why that generative model can produce impressive looking outputs at first, but they always fall apart because after you get the initial flurry, you start losing coherency very quickly in some cases. So, like I say, you can't.
Terry, if you allow me to comment something there, several years ago, Andrew Wills proved the Fermat theorem, and that theorem requires different branches of mathematics. It was not on a single branch of mathematics. So I wonder if the ML systems could help in terms of system analysis, where the mathematicians may not have enough knowledge on other branches, and therefore using systematically to gather knowledge from other branches, using MLs in order to develop his own proof. So I think that in that sense could be useful.
Yes. Yes, in fact, what you just hit on is exactly why these systems do have utility. Notice I didn't say that LMs are not useful, although I said the way they're being used now is terrifying. But they have uses. If you look at the human genome, the genome projects, AlphaFold. AlphaFold used carefully curated LLMs to help do very much what you just described, which is you have this huge database of DNA. No human can comprehend all that data. But the LLM can use that holographic mechanism and say, oh, I see similarities here, there, and yon, and all sorts of pieces. And all of a sudden it comes out with a protein folding strategy from some weird little bacterium that has nothing to do with the organism you're looking at. And you go like, wow, hey, that does it. That solves the problem. And this is where the large language model, the large data model can be very useful. The danger is the misuse of it. So yes, you can help on the mathematics, but boy, you better be careful if you let it start deriving your theorems for you. If you use it for the access thing, then it has a powerful reminder characteristic. But then you also get into this hallucination issue, and this is where the lawyers are the canaries in the mine. It can get really scary very fast because it'll come out with some theorem, and this will happen to the mathematicians. It will come out with some theorem that says if it's an unguarded version of just, again, that all sorts of technologies going on here. If it's an unguarded LLM and the mathematician asks for, some theory, some proof that it'll come out with something and it'll look good, but you better be very careful about whether it's real. There are so many cases of lawyers getting bit that way. They come out with some document that looks perfectly reasonable. It's got all the references, it's got the citations, everything's relevant, looks beautiful, and half of it's made up, or more than half of it, and the other half is damaged. So using LLMs for mathematical proofs, this is why I go back and said I wouldn't trust one as far as I could spit. If that's what they're using it for, no, it's not going to work. If they're using it for retrieval of information to find facts that they're unaware of, with cautions and with sufficient care, they make good retrieval engines. But this is a hard problem for these retrieval engines. They work best when they're trained on you and anybody else. As soon as you deviate away from retrieving knowledge from yourself that you trained it on, you start getting deviations. So when you go out for a general scan, yeah, it's going to find some good stuff for you, but you got to watch out for the poison in the pill. So it'll be interesting to see how this plays out in mathematics. But for any mathematician who wants to use an LLM to help them on the development of a theorem, like what's going on right now with Navier-Stokes, boy, I'd sure look at what's happening to the lawyers. I think that's such a point in case of the dangers of these systems.
Yeah, thank you. I'll learn. Caution. Yeah, thank you.
So what is a good way of using LLM? How can it be useful?
The model I always point to is the AlphaFold. AlphaFold they make no pretense. It doesn't actually fold the proteins. It doesn't know how to fold the proteins. So it's a bit of a misnomer, but it does have a huge database that's been carefully curated, and it can find out these patterns and just produce an enormous number of, okay, this is what the protein looks like, and it's right. So absolutely is models out there, and that's the one I point to is look at the LLM literature, and I think you can get a better idea of what they can and can't do. Even in those cases, there are, personally, I would use one as an exploratory mechanism and then convert it into more traditional software because they're also very, very incredibly energy hogging machines. And often once you find something, those rules can be encapsulated in much, much more compact form. So I think, LLM compilers could be a good future technology for some of these folks.
And so you mentioned about other AI models that can do better job as LLM. So can you give me some reference so that I can look for those?
Reference to which? I'm sorry, I didn't quite catch that.
You mentioned about some AI agent or AI model that can do better job than LLM.
Oh, I think the one I mentioned was it DeepMind? I think some of the DeepMind work, which was a few years ago, was good. DeepMind comes to mind. The predecessor to AlphaFold was one of the most remarkable AI explorations. And when it AlphaGo, the one that took the game Go, it actually started deriving strategies that no human had ever thought of after just a couple of days of training. And that would be an example of AI technology. That's the only time I've ever read about an AI technology. Actually gave me a little bit of a shiver, going like, oh my gosh, this thing is genuinely, beating the pants off the humans. But it was a very constrained problem space. And the reason they called the other one AlphaFold was really marketing, because AlphaGo was so successful that they used the same name for AlphaFold to give a little bit of a same resonance with that idea. General intelligence is just, I don't know of any case that I would call even close to general intelligence right now. What always happens is scaling. The scaling fails. So, and this goes back 40 years. Oh my goodness, I can remember examples of interesting problems, and we'd always have this little qualifier and say, yeah, except it doesn't scale. So, you do a toy problem and you try it and it looks like the system's really smart, and then it fails. And by the way, one of those failures, like from 40 years ago, was small language models, which failed miserably. they they did not work. They would produce outputs that looked like they might have something behind them, and then as it got larger, it vacillated between producing just rubbish and plagiarism. Which are, lo and behold, the large language models aren't that different. You vacillate between chaos and plagiarism. So tricky ones in that. But again, the AlphaFold AlphaGo was a remarkable little effort. I don't know. I'm hoping to get some updates. I'm going to I'll get to attend some reviews coming up in a couple of weeks, and I'm very curious to see where some of the research groups are going with some new AI approaches. So there's nothing out there even close to general intelligence right now. That has been, it's unfortunate how it's been turned into a marketing ploy because we don't have that. It's just not there.
Oh, I have a last question. I'm working on a project where I'm trying to use Markov chain
Yes.
theorem to predict to build age-default models.
Yeah.
And I'm wondering if someone can give me some references I can follow.
Oh gosh, Markov
Like
Markov chain literature is huge, and it's a very good technique. It's been used. I remember I commented to one of my co-reviewers once. He said, "If I see one more Markov chain proposal, I'm gonna throw it out the window." There's a period where just everything was Markov chain for a while, because it is a good technique. I mean, it does. It's a great way of ferreting out information in situations of uncertainty. I can't immediately point you to a good Markov chain literature, but I know it's out there. I think with a little bit of maybe some comments or notes, I can find something, but I have not investigated that area in the last couple of years. So my knowledge is a little bit stale on what's the latest on Markov chain. But again, it's a great technique. And even just doing some Google searches on that, you should be able to find some pretty good reference information. And then you just want to dig into some of the earlier sources. Often is a good way to get a deeper understanding of the technique.
Okay, thank you.
Actually, Chuba has a follow-up question. How are transformers different from Markov chains?
Oh, very different. Markov chains are a structured way of reasoning when you don't have a full knowledge. It's a you've got a mask, you've got you're Plato in the cave. You see shadows, but you don't see the full thing. The Markov chains accumulate those probabilities over time, and they converge to some degree of certainty and say, oh, here's a model that does a good job of producing that. The large language models are they're pattern finders and they're pattern smooshers. They look for patterns. When they find a pattern, they record the pattern. It's very holographic, very much like a hologram, and just munge it all together. They don't try to converge. Well, they do try to converge in the sense that they try to munge everything together. But Markov chains, you're looking for precision. The large language models, the other way around. The example I always give as an example, as a negative example, if you train a an LLM on maps, and you've probably seen some examples of this, maps and alphabets. These are some of the little no-nos that LLMs do poorly on. If you train it on a map has a lot of a lot of text, and has a lot of lines. And the trouble with the LLM is if it sees a line next to the letter N enough times, like edge of a boundary of a country next to Nebraska or some state or whatever, The LLM will conclude, oh, that's a good pattern. I'll use it. And you'll see this ridiculous map where it has new letters that don't exist, because that's a level of non-comprehension that goes on in LLM. It doesn't even realize that that pattern is completely bogus because it has no overall context. Markov models would go in the opposite direction. They would say like, oh, no, I got to refine this until I see the combination. Oh, that one works. Markov models work towards understanding, whereas LLMs just work towards averaging. So they have, and as in many things, there's some superficial similarities and they can use some of the same technology, but the goals are very different. So if you got a choice between AI models, definitely go with Markov models. Don't go with the LLM for building a model. For retrieval, that's where the LLMs shine. You know, Markov models are not good for retrieval, but you can do some good things with the you can do some good things with them.
I noticed Robert Becker has a comment. He said, I have forgotten that the gluons were thought to be massless, since the strong force is short range. That is
Right.
usually the hallmark of massive mediator, as in the weak force. Given that the Jave co-authored the famous treatise on constructive quantum field theory that features the asymmetric structure laid out in the problem conditions that is posed in this way is not entirely surprising.
Yeah, that gets right at the heart of why this was one of the problems that they picked. Is there is a real physics. I remember thinking the same thing back when I first started studying the standard model. I'm going like, why are these things massless? Because they sure are short range, and the reason is that the models could not give a reason to give them mass. They could not find a good model excuse for giving them mass. Whereas in the case of the electroweak force, they had abundant reasons for giving those mass. That worked out fine. But in the case of the gluons, they just kind of like, don't know why. And so the challenge is good for that reason, that if they can find a more fundamental reason, a more fundamental theory of why that happens, not really a math model. I would call it a theory. I wouldn't call it a math model, because the theory may be not even close to being, provable in the sense of usual, but that you usually think. But you can get a model that does a better job of predicting that, and that would be a marvelous thing. And that's why I say completely seriously, yeah, you may not get the CMI prize, but if somebody can solve this problem, they ought to get a Nobel Prize, and probably would, because that kind of a model would have power that we don't have right now.
And Robert has another comment. Use of computers in mathematical proofs have controversy that goes back well beyond LLM or even utilization of AI, as in the proof of four-color theorem by computer.
Yes, absolutely. And those uses, when you're not in the LLM turf, you can do marvelous things to help on proofs with computers. And it's just that you want to be a little careful about which feature of the proofs you're using. The proofs were rigorous software, carefully validated, carefully checked, and essentially proven mathematically to give the right answers for what they would do. And the reason those proofs are accepted as being valid was because essentially they had proved the code that did the work. And LLMs are just the opposite. They're just tea leaves. I mean, they're not proving anything. They say, "Oh, this sounds good," and they're terrible about that. They just love to give you the answer. They train on you to give you the answer that you want to hear, and that can fool anybody. So it's a very different type of computer assistance. And if you're using well-verified conventional software to augment the proof, and if you can figure out a way that you can use the LM where you still have that boundary of provability on the software itself, yeah, you can do some good things. But yes, and this is one of the things I don't like about the use of AI for LM. There's so many good technologies that are out there, they're in use, and everybody thinks that's all the same thing, AI now. And that's unfortunate, because this is not a good representation of the real world of AI, of what's possible. There's good technology out there. It's very helpful.
Actually, Helen said that called this another question from me, and that's actually correct. It was. I asked a couple of questions, or not. I made a couple of comments early on in your excellent presentation, but I didn't hear any. I did not hear you give a response to them at all. Did I miss something, or
Well,
that
what
was
was the
on
question?
that was on the constructive quantum field theory of Glimm and Jaffe?
I'm yes, they did ask that, but I'm not really familiar with the Jaffe work, so I would be reluctant to comment too
Yeah,
much.
I was commenting on why you presented a list of axioms, basically a list of names associated with axioms, Osterwalder, people like that, and I was commenting that Jaffe apparently is one of the authors of this problem that you presented,
Oh yes, yes,
co-authors or one of the early responders to it. And I'm pointing out that he is the co-author of and founder of the constructive quantum field theory thread or subdiscipline within quantum field theory, which tries to mathematically axiomatize and improve quantum field theory from fundamental axioms.
yes,
And
and
so I said that's why you would see in that problem that kind of a presentation and statement of the problem,
yes,
because that was his entire orientation. He and Glimm. So they basically have mathematically axiomatized and try to put quantum field theory on a firm mathematical foundation. If you read their treatise, it's
yeah.
entirely proofs. It's
Um,
a really excellent book, but
uh, Ataya speaks highly of that book. In fact, I added it into the references. Um, I think it made it into my online copy of Ataya's. If you look on my website, I've got a copy of. I did a transcript of Ataya's entire talk because I thought it was a really good talk. And one of the things I did was I expanded out the reference to that book you're talking about. So and it's interesting. He has a good description. He says like, well, if you want to take this approach, you can start there and start, clicking away with that. But Ataya also said you really ought to, he was kind of, you could tell he was leaning towards saying like, don't do just that because there's a lot of manual labor that goes very slowly with some of the approaches with that. Gross is much blunter. Gross complains bitterly about how many of these huge models have just such diminishing returns in terms of actual physics insights. So, and of course, David Gross's viewpoint is going to be the outlier on those different
that is
perspectives.
correct. It is because of that entire the philosophy behind that approach. Every little thing has to be proven, and it can
Right,
you've got
right.
your theorems and your corollaries and lemmas to extremely detailed level. So yes, but it's a rather fascinating way of doing it, and one would be thinking of departures from that. How would you change those axioms to chapter 6 of that book, particularly? How would you change those axioms to fit other types of theories or models? I would have one question for you, separate from that, which I'll briefly broach before we get too much later. I have been listening to several of your lectures, especially on issues of infinities and infinitesimals and lack of singularities and things like that. So what I'm wondering is, from that perspective, you propose a model in which there is an inherent cosmic censorship hypothesis to the universe. So, if, for example, the supposed singularity at the heart of a black hole cannot exist.
Yes. In fact, in the case of I think I even have a couple figures out there that I do not believe there's anything inside of black holes. I think if you look at all the dynamics of black holes, all the dynamics, including evaporation, occur at the surface. Now, here's an interesting question. If all the matter in a black hole fell through to a singularity and maybe, I don't know, went out in some other universe, how does that matter get back to the surface to evaporate? And if you look at the magnetic dynamics in black holes, which they have, and you say that all the matter fell into the singularity, there's nothing there. How did that happen? The history of black holes has just been this amazing ping pong match of different viewpoints of what's going on with that. My own personal description, what I would hypothesize, nothing more. I'm just a computer scientist out there. So,
I would,
what I would hypothesize is that you're actually magnifying the fabric of space-time to such an enormous degree inside of the black hole that there's no room for particles there anymore. It's just like if you imagine space as having a granularity, which it doesn't, but it does have a scale. But if you imagine that the scale factors, the whole, it gets into actually some interesting scale issues on the whole physics. But what I would propose is that the interior is actually a scaled up version of space-time that just literally doesn't have room for anything. So it's a hard boundary. It's a hard barrier. So things that go into it, and that would change the dynamics of black holes. For instance, on type 2 supernovas, when they collapse, after a certain point, they would not collapse into the black hole anymore. They would bounce because there would be a certain point where the black hole's surface, the event horizon, which is would look the same. The event horizon looks the same in all this. That doesn't change. But after a certain point, it just said, no, I can't take anymore. And, it goes back out. So you could get a rebound effect with a null interior black hole that you wouldn't do it. But yes, I am emphatically, I have to be self-consistent. If I say that the structure of space-time is created by these relationships of material particles and energies, then a black hole has to be a set of those relationships on the surface. I had a really nice, Tehuft is a very nice fellow. He actually, tolerates talking to folks like me. So I had some interesting conversations with him where I was just, by email conversations, talking about how his momentum interpretation of the surface of the black hole could be interpreted as a black mirror banding effect, that essentially, just like electrons form bands in ordinary matter, that you could have an entire band of protons, that they would be delocalized in conventional space, and that they would be in momentum space, just like electrons are. So you can get some really interesting potential dynamics on the surface of a black hole by doing that. If you assume that, and again, actual data, we've had stars, multiple stars fall into black holes, and they come back out 10 years later. So this is not that's actual data, which has turned into a consistent trend. So if they're all falling into the black hole, why are they coming back out? And I think a more reasonable hypothesis is simply that they go into slow time. They go into extremely slow time, do a very slow orbit, and then come back out the other side. So it's fascinating stuff going on, and all sorts of distortions of space-time as defined in that black hole. But I don't think singularities are one of them. I think that's I
there
think
is a, you raised electronic band. That's rather interesting because some of the more recent theories of what you asked about, which was the evaporation process. I
yes.
mean, traditionally, the evaporation is not that something comes back out, but that something, your pair creation, and one pair goes out, one pair goes in, that effectively induces the evaporation uh, of what by what's actually going in, less so than what's coming out. But more recent theories have actually looked at models of black hole evaporation, in which it's similar to what happens when you have a superconductor, uh, superconductors too, a superconductor, normal superconductor layering effect. And basically, there is a kind of like a conversion mechanism that goes on inside, and then it gets sent back. It then gets sent back out. So it actually, this is kind of like considered a superconductor model of what's actually going on inside a black hole. But that's interesting. I will. I
Do
don't
you
want
have
to
a
belabor
name?
this too much,
Do
but
you, do you have a physicist or a name for that, or a
yeah, I
super?
can. Yes, I can. Let me. You go on with this. I'll look it up in my records, and you.
Yeah. I would
I'll
love
give
to
you a
read more
name.
about that, because I think and again, Tehuft is interesting because I don't think Tehuft believes in singularities either, which is interesting, because when he talks about his antipodal model, he's really kind of saying like something goes in this side, antipode just means the other side, and it just kind of goes around over these momentum states. I mean, it was his work that inspired me to think that there's interesting, and these would be, I don't know if they'd be superconducting states, but they would certainly have some very interesting properties because the idea of a band conduction of protons is an intriguing concept. And also, this idea of black holes, black mirror effect. When you touch a mirror, do you get burned? No. Why do you not get burned? Because if you touch a piece of silver, that's a good example. Touch a piece of silver, why do you not get burned? Because the electrons that are at the surface of that metal are at a temperature in the X-ray range. They should kill you, but they don't. Instead, they're cold. And why are they cold? Because they're in momentum space. They're delocalized in ordinary space. They cannot contribute to your little tiny XYZ finger touching it there. They're scattered over the whole thing. Think how well that fits with the idea of a black hole, because a black hole has this all near absolute zero temperature and yet holds incredible energy. So the idea of thinking of these as delocalized energy effects actually works very well with a black hole. So it's cosmic mirror effect is what you could go through. So I would love to see that literature, because I think there's some interesting potential. And again, black hole literature has changed so much over the decades. They have an absolutely certain model that will last for 10 years, and everybody goes, "Oh my gosh, we're wrong," and then it all falls apart. They try again. So there's not as much certainty on some of that as you might think.
I have
That's interesting.
have some references for you. You've heard of I don't know if you've heard of Andrew Jordan.
Jordan?
Jordan, yeah, Jordan. He's out in Europe. Well, no, actually, I guess it'll be more some of these neck of the woods. He's out in California at University of Rochester, my alma mater, and also Chapman University, and Srinath Manikandan, who was at the well, at that time was also at Rochester. This is from 2020. Black holes as Andreev reflecting mirrors.
Oh, wait, what? Say that again?
I couldn't hear you.
So, can you say that again? What was that title?
Yes, black holes as Andreev reflecting mirrors. And Andreev reflection involves those three layered systems I described, two superconductors with a sandwich around a normal conductor.
Oh boy,
Uh,
I want to read that one. I mean,
yeah,
uh, I
that's
for
an
years.
X archive paper. I can X archive 2007.09467 version 2 from September 10th, 2020.
Ooh, okay. I gotta look that.
Basically, a microscopic quantum description of Hawking radiation, uh, trying to solve the usual quantum information paradox.
Yeah, yeah.
And it's quite fascinating how
Oh,
they.
I got to read. I've been on this cosmic disco. I think I've called them cosmic disco balls for years now. And it goes back. I believe I've got a track record before 2020. So I mean, it's been a while. I'd have to go back and check those conversations with Hooft. But I just think I think there's some fascinating potential in that approach. And like we're saying, uh, delocalization in momentum space can hold enormous energy and yet give you cold temperatures. And I just can't get around the fact that sounds so much like the surface of a black hole. Is these enormous energies, low temperature. It's an interesting combination. So yeah, thank you for that reference. I look forward to reading that one.
Interesting to hear your opinions on it. Yeah.
Okay, thanks.
Actually, I noticed Maya, she posted the link on the chat to the
Oh,
article. Black
let me.
hole as Andrew reflecting mirrors.
Oh gosh, this is.
Yeah, you can read about the article and you can talk about it next year.
Well, actually, I have a talk on general relativity coming up next year. And as usual, I'll be coming with some unusual perspectives on that, where maybe it's not as far away as we had. Let's see. I'm trying to find that reference. Black holes, yes. Okay, let me get a screen copy of that. Got it. Thank you both. That is like I say, that is an area of great interest to me. So, and also I just think I think it's a productive area that could do some good things. And it's just more interesting. It's you know, when you get away from, I think the universe is more complicated than just general relativity. So there's, and general relativity gives a very simple black hole, but boy, that sure doesn't seem to be what we're seeing experimentally or in some papers like that. Anyone else?
Yes, I noticed a question from Chuba. He asked, how come the four-color theorem was too complicated for combinatorial methods?
Oh, it's just the four color, the number of combinations for a human was just too large. It's just, there's so many things to explore. And sometimes the universe provides you with a shortcut and you can collapse everything into one little equation, which is some of the greatest mathematical finds of all time. But other cases, no, it's just complicated. It's just, and that four color theorem seems to have been one of those cases where it just there's just too many combinations for one human mind to comprehend or even have time for. But if you write a program and the program's well verified, I have no problem with that. I think that's a powerful strategy. Might as well, you know, computers and humans can do great things together if we make good use of them. So as long as we don't let them lead us, if we let them lead us, we're in trouble. And I don't mean human sentient side. I mean just because computers are dumb. Don't let them do the inside part. Let them do the hard work, you know, and I think we get a better outcome.
And George Siplen, he comment, Appel-Haken four-color proof was careful enumeration of many special use cases.
Yes. Yeah, in fact, I remember there's a story, I think when he first did it, he had made a comment about how he used his own kids to help find examples of use cases. And he got a lot of flack for that because we were saying, "Oh, you used your you used your kids." You know, that would be an example of where LLM could be handy if it is just helping you explore the space and everything it does is carefully checked. Yeah, you know, get some help on going through that. Yeah, it was that was a long time ago now. Wow, wasn't it? I remember when that first came out. There was a lot of controversy about that.
And Chuba has a second question. Is what you are saying similar to the Eddington limit?
The Eddington limit?
Eddington limit, yes.
Eddington limit. I know some of Eddington's work and what I don't know what the Eddington limit is. So you have to clarify that for me. I'm not sure what that's referring to. We'll wait a little bit here for a reply. I'm gonna try to look it up on Google here real quick.
Yeah, me too. Yeah, Eddington limit, also known as the Eddington luminosity, is the maximum luminosity a star or other astronomic
Maximum luminosity. Oh, okay. Okay. Yeah, that sounds like it's related to collapse, black hole to supernova collapse would be what I would. Eddington did some fascinating work. He got himself in trouble with some things he said with other physicists, but he also did a lot of really good work. And yeah, this is certainly part of the issue that goes on with supernova collapse, type 2 supernovas. So, but what was the question? I'm not sure if I caught what the question was.
Chuba's question is what you're saying similar to the Eddington limit?
In the case of no, actually not. The case of the black hole, where I was talking about space granularity amplification, is I'm hypothesizing a totally different phenomena, where space-time itself is And the easiest way to think of it is just imagine space-time being magnified to where an atom is the size of the entire star. So then you only have room for a proton and an electron in the entire interior of the black hole. So that's not a radiation limit. That is a space-time structural limit that the concept of traditional XYZ space-time just is so bloated that it can't hold anything. It becomes a barrier instead of an entry path. And the mechanism for doing that would be via the momentum states on the outer, what we think of as the event horizon. So yeah, that's an interesting connection, though. I hadn't thought about that, but that's a yeah. This would be a different phenomenon. That's an energetic phenomenon with a high degree of instability as you lose that. The black hole mechanism I was talking about would be an extremely stable effect that could outlast the universe, because once the magnification is in place, it's just like that's the new definition of space-time. So, as far as that black hole is concerned, it says I got no room in there, and it keeps everything out.
Yeah, Chuba at Egerton mass limit is a limit at which black holes can absorb.
Yeah, there is some kind of a limit on how fast black holes, and that's conventional. That's been around for decades. There's a limit on how fast a black hole can absorb matter, which I think is based in part just on literal, area. There's a size limit. You got a tiny black hole, and you got a lot of matter falling into it. Something's got to give at some point. So I think that's been around for some time. The rebound effect I was talking about would be a little different. It would be some kind of a prediction that at some point, even for matter that's nominally has room to fall in, it would just bounce. That the black hole would not be a perfect absorber in some cases.
So far, I haven't seen more questions. So Joe said this is an excellent section.
Oh, well, I'm having great questions. It's a lot of fun. We're covering, we got into a fairly good LLM tangent there, but anything else?
And Lou says it's really interesting talk. Thank you.
Well, thank you all. So thank you, Helen. I always enjoy these monthly talks. These are a lot of fun.
Yes, and you have another talk on November 8th and December 6th, and also
Yes.
January 17th.
This is keeping me busy in my retirement, because these are a good challenge. These are a good challenge, and I like being my own boss. And these are worth trying to, like that last one about digging into the infinitesimals. That was interesting because it brought up a lot of issues that I had not thought of on that, and these are good areas for some interesting research.
Yeah, and may I say we have covered a lot of topics today.
Yeah, yes, it's been a potpourri and diverse and good coverage.
Yeah. So any other last minute question?
Just say thanks, Terry. You're teaching physics to the world.
Oh, well, thank you.
Yeah, we are all over the world.
How do you pronounce your first name, by the way?
Gaetano.
Gaetano, is that right?
Yeah, Gaetano, yeah.
Gaetano, okay.
Yeah, I'm based in England, UK.
Ah, okay.
Yeah.
Okay. Yeah, getting to see a number of familiar faces. So, well, thanks everybody, and I guess we'll wrap it up then.
Sure. Thank you for coming. Looking forward for the November and December talk and January as well.
Okay.
Thank you.
See everybody then. Thanks.
See you.